In our previous lesson, we looked at calculations involving electrolytic conductivity or electrolytic conductance. We did a number of examples on them. I told you for this episode, we shall basically be looking at factors affecting electrolytic conductivity. Factors affecting electrolytic conductivity, kappa. Now, there are basically two factors that do affect electrolytic conductivity. Only two factors that we shall be seeing. One of those factors is concentration of the solution. And the second factor is temperature of the solution. Concentration of the solution and then temperature of the solution. Those are the two factors that affect electrolytic conductivity of electrolytes or electrolytic solutions. Now we shall look at each of these factors in detail. How does concentration affect electrolytic conductivity of a solution? That's the first factor we should see, the effect of concentration of the solution. If I do have a sketch of a graph, I'm to have a sketch of a graph, which graph is I want to try to be a bit more accurate in sketching, but it can't happen. So I will try to sketch something like this. If this is a graph showing concentration of solution, of course the concentration is usually in moles per liter. I think this should be on the x-axis. Concentration in moles per liter. And then on my y-axis, I have the electrolytic conductivity, K, or kappa. I think you know its units. Per ohm per centimeter. If I'm to sketch this graph, as concentration increases, the conductivity increases. It will increase up to a given maximum and then decreases. Shall have a sketch of that kind. It can decrease up to this line again, but that's the kind of graph you can usually have for the effect of concentration. Now we are yet to explain why this is so. First of all, we state the trend. This trend here I'm giving is that of a strong electrolyte. a strong electrolyte, like maybe sodium chloride, what shall we say? We shall say that as concentration increases, conductivity or electrolytic conductivity increases up to a maximum and then decreases. That is the trend. As concentration is increasing, the kappa is increasing up to a maximum and then decreases. Why is that so for a strong electrolyte? What you need to know that for a strong electrolyte, whenever concentration increases, if this is a solution that is dilute, and these are the ions, sodium ions and chloride ions, at a dilute concentration, when the concentration is increased, those ions are so close to each other. So close to each other. And what you should know is that for conductivity to increase, there is increase in what we call ionic mobility. Mobility of ions. The ions must be moving very fast. Very, very fast. The higher the ionic mobility, then the higher the conductivity. If those ions are moving at a low speed, then there is a low conductivity. So whenever you increase the concentration, here, there is what we call ionic interference. Ions interfere with themselves because the total number of ions per unit volume increases after increase in concentration. So in the ionic distance, the distance between ions is what I call ionic distance, decreases. Ionic interference increases. Ionic mobility decreases. In other words, what should you talk about when you're explaining this? Talk about the number of ions per unit volume of a solution. Talk about what happens to interionic distance between separate ions. Talk about what happens on ionic interference. Talk about what happens on ionic mobility. Then relate all those to electrolytic conductivity. So we shall say, as concentration increases, conductivity increases up to maximum and then decreases. Why? Because the increase in concentration increases the total number of conducting ions per unit volume. Increases the total number of conducting ions per unit volume of solution. Why do they increase? Since the electrolyte, this being a strong electrolyte, is completely ionized. Is completely ionized at all concentrations. Therefore, what happens? Ionic distance decreases. Ionic interference increases. Since the interionic distance has decreased, then the ions will interfere with the movement of each ion. So ionic interference increases, ionic mobility decreases. I thought you talk about all those three terms. Stop. And then you say this decreases electrolytic conductivity. I think there is something missing. Okay, we saw the trend. There is an increase here. We talk about that increase, then we talk about this decrease. Why is there an increase here? The increase there is due to the total number of ions per unit volume increases. Okay. So as concentration increases, the total number of conducting ions per unit volume of solution increases, and then you say this increases the electrolytic conductivity. Since the electrolyte is compared at all concentrations. Then you also tell us that interionic distance decreases and interference increases and mobility decreases, and then you say this decreases electrolytic conductivity after this maximum. So the increase here is due to increase in the total number of conducting ions per unit volume. Total number of conducting ions, since the electrolyte is always completely ionized. Then the decrease here is due to decrease in interionic distance due to increased concentration, leading to an increase in ionic interference and reducing the ionic mobility. Are we together? I hope so. So that's all about the variation in electrolytic conductivity with the concentration for a strong electrolyte. For a strong electrolyte. How about a weak electrolyte? What happens if the electrolyte is weak? I want us to see what happens there. Now, for a weak electrolyte, you will have concentration increasing. So for a weak electrolyte, you will have, okay, for weak electrolyte, we will have conductivity increasing with increase in concentration. Actually, it's the same trend. It's the same trend as a strong electrolyte. So we have what we call electrolytic. So the electrolytic conductivity here is varying with concentration of the electrolytic solution. And the graph is the same. So our explanation will still remain the same explanation. We shall say as concentration increases, conductivity increases up to a maximum. Electrolytic conductivity increases up to a maximum and then decreases. Why? As concentration increases, the total number of conducting ions per unit volume increases. We have already talked about that. As concentration increases, the total number of conducting ions per unit volume increases, and then you say this increases the electrolytic conductivity. As concentration increases further, what happens? As concentration increases further, what happens? That's where the difference is going to come in. So we shall say electrolytic conductivity increases up to a maximum with increase in concentration. It increases up to a maximum with increase in concentration, and then decreases. Why is that so? For a weak electrolyte, you're going to see where the difference will come in. So you say as concentration increases, the total number of conducting ions per unit volume increases. Total number of conducting ions per unit volume increases. And then you say this increases conductivity. This increases electrolytic conductivity. So far we are up to that point, this increase here. Then why this decrease? For strong electrolyte, we said this decrease due to a decrease in ionic distance of separation, and then increase in ionic interference, which leads to a decrease in ionic mobility. And that leads to decrease in electrolytic conductivity. How about for weak electrolyte? The weak electrolyte being slightly ionized in solution, there is always an increase in unionized molecules of the electrolyte. The degree of dissociation decreases, and the number of conducting ions per unit volume of solution decreases. That's the only difference we shall talk about here. Okay, so you say as concentration increases further, as concentration increases further, this is for weak electrolyte, number of unionized molecules that are unionized, because this is a weak electrolyte, of the electrolyte increase. Degree of dissociation decreases. Number of conducting ions per unit volume decreases, leading to a decrease in electrolytic conductivity. Questions about these sketches have never been asked, but you never know. One time you may meet it. Usually the questions that we meet in exams are those of molar conductivity. Okay, so that's the explanation you would give for this kind of graph. Talk about the degree. Actually, whenever you're talking about a weak electrolyte, your answer should have something about the degree of dissociation. your answer should have something about the degree of dissociation. That's all about the effect of concentration on both electrolytic conductivity of a strong electrolyte and electrolytic conductivity of a weak electrolyte. In both cases, the trend is at first the same. Even in the second case, it is the same. There is a decrease, but the explanation only changes in the second phase. The strong electrolyte, I've emphasized, we talk about a strong electrolyte. I've emphasized what we talk about, and even the weak electrolyte. What have I said? I've said that for a strong electrolyte, emphasize number of ions per unit volume. Talk about interionic distance in the second phase of the graph. Talk about ionic interference. What happens to the ionic interference? And then talk about what happens to the ionic mobility. When you come to the weak electrolyte, the first phase is the same, but in the second phase of decrease, what do you talk about? Talk about the unionized molecules, their number increasing. Talk about the degree of dissociation decreasing, and then relate that to electrolytic conductivity. Then you'll be good to go. I think that's very clear. We can now look at the next factor affecting electrolytic conductivity. That's factor 2. Factor 2 is temperature of the solution. Temperature of the solution. I'll begin with a strong electrolyte. So usually they separate the question and tell you to talk about a strong electrolyte, or they leave it open. If they leave it open, talk about a strong electrolyte separately. Also talk about a weak electrolyte separately. We are looking at the effect of temperature on electrolytic conductivity, not molar conductivity. For molar conductivity, we shall later see this effect. So, of course, the increase in temperature will increase the kinetic energy of the conducting particles or the conducting ions. As we said, for conductivity to occur, usually the solutions have are usually ionic. Most of the electrolytes are ionic. So as temperature increases, the average kinetic energy of the conducting ions increases. Remember, our electrolyte is usually dissolved in water. That's what I want you to know. Usually dissolve the electrolyte in water. Put the sodium chloride here solid to form the electrolytic solution. Now, if we are having such a solution, whenever you increase the temperature, the ions are going to start to move at a faster rate to increase their kinetic energy. As they are moving in water, which is here, they always face a resistance force called viscosity of water. So when you increase the temperature, this viscosity is also decreased. In other words, I want you to talk about, if you're talking about a strong electrolyte, talk about the kinetic energy of the conducting ions. Also talk about what happens to the viscosity of the water. Then talk about ionic mobility. So for a strong electrolyte, what happens? You say increase in temperature increases the kinetic energy conducting ions. Viscosity of water. This viscosity is to the ions of the conducting solution, conducting electrolyte. So viscosity of water decreases. And then ionic mobility, cannot forget this, increases. Therefore, increasing electrolytic conductivity. That implies that electrolytic conductivity increases as temperature increases for strong electrolyte. Because increase in temperature of the solution increases the kinetic energy of conducting ions, decreases the viscosity of water to the ions, increases the mobility of the ions, increasing the electrolytic conductivity. Hope that's very clear.
Yes, teacher.
What happens for a weak electrolyte? Whenever we talk about a weak electrolyte and we are talking about temperature, just as we saw in ionic equilibrium, when we are looking at the effect of temperature on pH of solutions. If you remember that, we looked at both. We looked at weak acids that ionize exothermically and weak acids that ionize endothermically. Then we related the effect of temperature on each of them. Okay. So for a weak electrolyte, increase in temperature, the effect of temperature depends. Effect of temperature depends on the enthalpy change which accompanies ionization. What does this mean? If the weak electrolyte ionizes exothermically, that its ionization involves production of heat, then effect of increase in temperature will decrease the conductivity, according to what we call Lochet-Elias principle that we are here to look at in chemical equilibrium. I think we looked at that topic. So when you increase temperature and yet the electrolyte is ionizing exothermically and it's weak, you're supplying heat to a reaction itself that produces heat. Then Lochet-Elias will have to work. Okay. So increase in temperature will decrease the electrolytic conductivity because the reaction is favored by, okay, we have the electrolyte ionizing. This is my weak electrolyte, ionizing in water to form hydrogen ions. Let me assume this is A plus water, form hydrogen ions, and maybe A minus ions, something like that. And the reaction here is negative, it produces heat. It will not be good for you to increase the temperature of such a reaction. When you increase the temperature of such a reaction, you're going to lower the degree of ionization. It will not ionize as it would if there was no increase in temperature. And that will lead to a decrease in number of conducting ions per empty volume, which will of course decrease electric conductivity because the degree of dissociation has been decreased. what shall we say? We shall say, for a weak electrolyte, that ionizes exothermically, or that ionizes with production of heat, increase in temperature decreases the electrolytic conductivity. I don't want you to confuse electrolytic conductivity with molar conductivity. We have to see molar conductivity. Increase in temperature decreases the electrolytic conductivity. Why? Because the degree, when you increase the temperature, the degree of ionization decreases. That's one thing that happens. The number of conducting ions per unit volume decreases, and then electrolytic conductivity, I've talked about that already. Conductivity also decreases. How about a weak electrolyte that ionizes exothermically? We also talk about that. It's the opposite of this. For weak electrolyte that ionizes endothermically, what does this mean? That for this electrolyte to ionize, heat is absorbed. It absorbs heat. So for it, it will be favored. The forward reaction will be favored. So you'll say increase in temperature increases the electrolytic conductivity. Why? Because the degree of ionization increases. Number of conducting ions per unit volume increases, which increases the electrolytic conductivity. Are we together? Hopefully, that's also a point driven home. Yes, there is a question. I would like to proceed to now factors affecting molar conductivity. Is there any issue to handle? Okay, that's fine. Then we go to molar conductivity, factors that do affect molar conductivity of electrolytes.